Hey, everybody. I was asked to talk about artificial intelligence, robotics, navigation, and the future of limb reconstruction surgery, all in about 10 minutes at the end of a very long week and a very long day. So I'll start with this. I think it's very clear that we are surrounded by artificial intelligence everywhere we go in life. And we are sometimes of the opinion that it's a new thing. It is not brand new. It has been with us for a very long time. And in fact, the Google algorithms that we use to search for things on the internet have been around for almost 25 years now. So artificial intelligence in daily life is there, it has been there, and it is certainly expanding rapidly. And you just have to look at any of your LinkedIn feeds to see that every second person or company is jumping onto this bandwagon. So what I thought I would do is to just look at, firstly, artificial intelligence and give us a quick overview of what that means, and then look at potential applications of these new technologies in the field of limb reconstruction in an attempt to just create some future-looking viewpoint, if you will. I found this article very useful, and it is a fairly understandable review of artificial intelligence in orthopedic surgery specifically. AI, the term was coined by John McCarthy already in 1956. And essentially what he described was a concept whereby one could create an algorithm that would be extremely good at pattern recognition with limited human input. So in other words, a computer that can recognize patterns without a human actually telling it what to look for. And that at its core is what artificial intelligence is. It relies greatly on the concept of big data and metrics. And we are surrounded on a daily basis by large amounts of data that get created, that get bandied about, and metrics that get measured that we are almost swamped in at some points. If you just look at a simple thing like an ankle fracture repair in an operating room, just think of all those individual steps, all the little time points, all the little variables that one can follow throughout that procedure. And it becomes very clear that once you start measuring those things, you're sitting with tremendous amounts of data. And what artificial intelligence is really good at is to mine that big data and try and find patterns and correlations and try and create sense out of the chaos in a way. It is also very good at cognitive unloading. So what it means is that we're not using human minds anymore to actually think of patterns, to look at patterns, to try and make sense of it all. We actually use a computer algorithm to do that for us. And this field at its core is really a convergence of computer science, maths, data science, and statistics. In a way, it is statistics on steroids using very sexy, cool algorithms. Right, let's make sense of it. If I look at this data set in front of me, it is maybe pretty, maybe not, but it is very clear that there's a scattering of shapes and colors across the screen. And if I start looking into it a little bit more in detail, I might notice some peculiarities. I might start noticing that every time that there is a red triangle, it is in close relationship to a green triangle. I might also see that all of those red-green triangle combinations are in the upper part of the screen. And suddenly we've created a bit of pattern recognition on this otherwise random picture. And that is really what artificial intelligence is really good at doing. The algorithms recognize patterns that might be invisible to the naked eye and start creating correlations between those, and then refining that pattern recognition up to the point where it becomes almost predictive, where you can almost predict, because of this pattern, that is what's going to be the outcome. And at its core, that's what artificial intelligence is. It's just a very clever way of doing that without human intervention. So let's say we have X-rays in our clinics, And we want to teach a computer how to recognize one of these two frames. So we would go about and we would tell the computer that, remember our little red and green triangles? That if we find a red triangle very close to a green triangle, in this case, the red triangle would be the side locking bolt on the TL hex strut, and the green triangle would be the spherical connector at the end of the strut. If we find these two things in close proximity to one another, it might mean that we're dealing with a TL hex device and not a TSF device. In addition, if these are attached to two rings, that means that it is a strut that we're dealing with. Mimicking in our previous example, the upper part of that graphic. So in other words, the three things we were looking at is the pattern was that we had a red triangle and a green triangle close together, and they were in the upper half of the screen. So in this case, the upper half of the screen is we've got a longitudinal strut that attaches two rings. The green and the red triangles are the side locking bolt and the spherical connector. And if we say yes to all three of those parameters, we're probably looking at a TL hex device and not a TSF device. And we can actually teach a computer to learn this. How that all comes together and the process of that learning happens as follows. So we start with big data, which is essentially the big data set out there. We create from that a data set that we want to input into our AI engine. So in this instance, it would be all the X-rays in our limb reconstruction clinic that pertain to hexapod fixators. This data set then gets fed into the AI engine, and the AI engine runs an algorithm that actually takes the data set and it measures it against the parameters that we've given it. So we told it that if the strut is attaching between two rings and it has a side bolt and it has a spherical connector, it is probably a TL hex strut. So the computer will now use that known parameters and it will measure the patterns that it comes across it against those parameters, trying to find chaos, or sorry, try and find order in the chaos. And it will then kick out a certain output. It will create an output. So it will tell us that I think that the following X-rays belong to the TL hex group. What we then do is we look at how accurate that computer was in that assumption, and we then refine the code or the algorithm to, in fact, become more accurate. Once we do that, we actually feed it back into the loop. And it's this loop that is known as machine learning. So you've come across this term, machine learning, that's what it means. So it's not really a learning process, it's actually a process of optimization of an algorithm. And that's all it is. Machine learning then serves the purpose of refining this whole algorithm or this whole process. And every time we run through one of these cycles, it is called an epoch. And for the majority of the machine learning developments, we run through somewhere between 10 and 10,000 epochs in order to actually refine the system, depending on the application. Now, you can imagine that that becomes extremely time and resource intensive to do that so many times. So another concept is to actually get the computer to refine itself and to actually change the code at that point on its own. And it does that, and that is called deep learning. So you might have come across that term as well. So deep learning is really where the code autocorrects itself to become more accurate. And that is called deep learning. And of course, that is a little bit of a black box because suddenly the computer codes itself. And it sort of makes most of us a little bit uncomfortable when it does that. I think as long as it's got a power plug, I'm happy. But yeah, so that's deep learning. And deep learning then also relies on really different layers of very interconnected relationships between parameters and data. And if you continue doing these little lines that I do here, you would start realizing that that looks like a reticular network of neurons, axons, and dendrites. And it that is what is known as a neural network. So in other words, at some point, the hierarchy of the organization of this deep learning algorithm starts looking like a brain in a way. It's got a neural network. And that's in a nutshell what that term also then means. Right, so the prerequisites to have a proper AI system is you need to have enough data and you have to have the data clean. You have to have processing power and you have to have lots of it. We measure processing power in terms of flops, and you need lots of those flops to actually make this work. And then you need a sound algorithm as a starting point, but the algorithm needs to be able to then be updated appropriately to feed back into this loop and create a new epoch. So common applications of AI in medicine and specifically in orthopedics are in these 4 fields. So firstly, in terms of diagnosis, AI is really good at pattern recognition, and it has been proven to be as effective in recognizing fractures on X-rays as orthopedic surgeons. It is probably more effective than the average radiologist at looking at CT scans for metastases. So it is really good at doing that. The second thing is in terms of decision making. So with all the data that we can feed into an AI system, it can start seeing correlations that we might not be even aware that exist. And because of that, it becomes a very powerful way of predicting complications or outcomes, prognosticating our treatment algorithms. And in a way, that is a very powerful application of this, because suddenly it helps us in our decision-making based on what it knows is going to be the potentially bad outcome. The next term I call technique execution, and that's really where we go into an environment of delivering care. So in our context, that would be surgery, and how AI then helps us to be more accurate, helps us to be better at doing what we do. And that is where the whole field of surgical robotics, surgical navigation falls into this topic. So it is a form of AI. It uses very advanced algorithms. It uses all kinds of fancy things, but it is at this level where that comes into play. Lastly, it also is valuable in administrative functions and research, where we can start making sense of huge amounts of data and try and create some order in that big data set and trying to become predictive in what could and could not work. How do we bring it back to limb reconstruction surgery? Well, firstly, in terms of diagnosis, we know that the AI engines are really good at pattern recognition. We know that we can teach a computer what something looks like based on the pattern. And once it can start recognizing patterns, it should not be too difficult for it to automatically pick up where a deformity is, where the optimal place is for an osteotomy, and indeed where we should likely place our rings in an external fixated context. And a lot of people are working in this direction, but yeah, it's not very far away when we'll have a completely automated planning workflow for complex three-dimensional plans. We already have some of that in the world of arthroplasty, where the templating solutions are becoming really intelligent at positioning things on our X-rays. In terms of decision-making, if we're faced with this interesting, difficult case, we could plug in the X-ray into an AI system in future, and it would kick out the most appropriate types of procedures or care pathways that would be applicable to this patient with the predicted amount of complications. And that can become a very powerful way of navigating this difficult world of medico-legal implications of what we do. In terms of technique execution, the concept of robotics and navigation, it's all around us. It's literally being pushed down our throats. For those of us who do not do arthroplasty, we do not get a lot of time to play with these tools. But of course, this is not a big jump to jump from making a tibial cut using a robot to making an osteotomy using a robot, or placing a wire using a robot. So the technology is there. It's just to create the correct algorithm to apply that in limb reconstruction surgery. Tied into this is the whole field of augmented reality, virtual reality, mixed reality, immersive reality, all these terms that we hear. Essentially, this is where we create a virtual reality that is superimposed on what we see around us, on actual reality. And that is what we call augmented reality. So something like a heads-up display that would allow you to manipulate things in three-dimensional space, but also to have those things link into real objects that the system could recognize. So you could have, for example, a situation where you are operating on a patient, but you would have your patient's preoperative plan superimposed on that limb already in 3 dimensions. And conceivably, an AI engine could then even help you to look at where you should place your osteotomy, where you should put your hand when you're drilling for a wire, and so forth. And this all relies on very complex software that exists in a computer that you wear on your head. It makes you look a bit ridiculous, but it works quite well. And there's a lot of us working in this field trying to bring solutions in this manner. In terms of administrative work, I think it goes without saying that we all need help with that. I think the opportunity exists for AI to really unlock vast amounts of data for us to use for research purposes, for optimization of processes, and also for optimization of things like billing. You could get to a point where an AI engine could watch you operate and it could pre-fill all the codes and the surgical steps that you've done into a document that becomes the surgical record, or that becomes the billing template to send an account to the insurers. So these are just some of the interesting aspects of artificial intelligence that are currently being developed, that are currently available in some instances. And I want to leave you with this question. You know, we are in a similar position as pilots are, you know, and when you fly back home after this course and you hear that the computer is flying itself and there's no pilot up front, would you be comfortable with that? The computer can probably do a better job than most pilots. But I think as surgeons, we're in the same boat, in that most people would still expect us to be involved in their care rather than just the computer. And long may that concept last. With that, I thank you.